It's a pleasure to have Edwin León Cardenal once again to keep telling us about real zeta functions and some problems in the study of oscillatory integrals.
Okay, thanks again for inviting me to this seminar. It's been nice to see you guys. Okay, so can you hear me well?
Mm-hmm.
Okay. So for this second talk, I want to start with the definition of what a local zeta function is. Then I'm going to explain a little bit some generalizations of local zeta functions. And at the end, I'm going to discuss a little bit of a couple of problems about local zeta functions and real oscillatory integrals. Okay, so last time we saw this definition just for the real case, but actually this is something that works for R or C, and it's called Archimedean local zeta functions. So again, you consider a k-analytic function and a smooth function with complex support. This is the notation for this guy here. This is the smooth functions with complex support depending on U. So to this pair f phi, you can attach the following parametric integral, that is the integral of the absolute value of f raised to the power c, where this sigma, sorry, is a complex number with real part greater than.
Okay, I'm gonna start the recording.
Sorry? Okay. So what we saw last time is that this integral converges in this half plane and defines a holomorphic function there as a function of the parameter sigma, okay? And this was the example that we show in detail last time, is the example of a monomial. So for this monomial, what we saw is that the poles of these zeta functions are given by these arithmetic progressions, okay? The ones given there, here. And at the end, I told you about this theorem, the meromorphic continuation of these zeta functions can be proved by a resolution of singularities. Okay, so the idea is that locally we have this morphism pi, and we can use this morphism as a change of variables, and locally we have monomials, and so for each monomial we know how the poles are. So in general, what we have is that the poles, or the candidate poles, are given by the numerical data of the resolution singularities. Okay. And there was a second proof of this result, of this meromorphic continuation of the zeta function, but this time this proof was using the theory of the Bertrand polynomial, and the result here says that the candidate poles are integer chiefs of the roots of the Bertrand polynomial. Okay. Again, the big open problem is to determine the true poles, because these tools just give you candidate poles. Okay. And this is largely open, this problem in general. Okay. So I want to make another connection with another very interesting object in singularity theory, that is the log canonical threshold. So you can define the log canonical threshold as the supremum of this index, this index here, this power, and you ask that this integral is finite. I mean, this function is f to the minus c. The absolute value of f to the minus c is integrable. Okay, it's locally integrable. This is one way of defining the local canonical threshold. And there is a lot of work of Lichting, Kolar, and Llano saying that the local canonical threshold is, for instance, the absolute value of the largest root of the Bernstein-Sato polynomial, and this is also minus the greatest pole of the local zeta function. Okay. Here we have an example of the local canonical threshold of the monomial that we were considering in the previous examples. Okay, so it is not hard to check this assertion from this expression and the one that and this one. Okay. Because in this case, these MIs are just one. Okay. Okay. So I'm going to move on. So there are some generalizations of local zeta functions. The first one that I want to discuss a little bit is the multivariate version. Okay. So in this case, there was this work was done by Sabat and then by Lesser, and they show that if you consider a tuple of L k analytic functions, F1 to FL, here remember that you can K it will be R or C. Okay. And you consider a smooth function with compact support, then you can construct the following integral. So here you put your function with compact support, and then you put several parameters, several powers of the absolute value of each one of the functions of the K analytic function that you are considering. Okay. In order to be short, I'm going to use this capital F to denote this better. Okay. So this integral is well defined when all the real powers of the real parts of the powers of the complex number space I S L are greater than 0. Okay. But the convergence of this integral is in CL. Okay, this is the key point. Sorry. So what Lesser shows is that you can use a resolution of singularities of this guy in order to prove that this local zeta function defined in an L-dimensional complex space has a meromorphic continuation. Okay. So in this case, the numerical data are given in this way, where this denote the multiplicity of the pullback of the of each Fi. Sorry, of each Fi, and this new denotes the multiplicity of the pullback of the differential form. Okay. So again, this strategy is the same, but you can split your data in this way. Okay, so this is the new thing here. So, but what we have is that, for instance, if the pre-image of this set is this set of divisors, then for each one of these guys, one has this linear form, and this linear forms gives you the region where this zeta function will be holomorphic. Okay. Sorry. And moreover, you can prove that this local zeta function, this is equivalent. Let me say that this is equivalent to showing that your zeta function in just one variable, in just one f, I mean, defines a holomorphic function when the real part of well, let me write it this way. Maybe you remember this kind of diagrams that I was drawing the last time. So this guy here, that is the greatest pole of the local zeta function, is the local canonical threshold, okay? And your function is well defined over here. So this is the version in CL of this statement, okay? And moreover, what we saw last time is that the poles were appearing in this region each time I was making I was iterating some process in the example that I presented last time. So in general, what we have is that you can have the meromorphic continuation to the whole complex plane, but appears on poles, okay? But there appears. So in this case, in the case of several, or of zeta function with several functions and several parameters, what we can show is that the poles are contained in a list of linear forms, and these linear forms intersects in some very precise way inside CL. Okay, so this is a set of CL. Okay. So this was the result of Lesser, mimicking the situation in the one-dimensional with just one function. And there was another, well, actually this was first. The meromorphic continuation, the proof by Sabat, includes what is called the Bernstein-Sato ideal of this function f. So when you consider this map, the Bernstein-Sato ideal is the ideal generated by the polynomials that satisfy this functional equation. In this case, the functional equation says that you consider here the product of all your fi to the power si, and then there exists some differential operator that gives you exactly this functional equation. Okay. So this is what Sabat showed in his article. He shows that this is a non-zero polynomial, and moreover, the meromorphic continuation of the local zeta function is contained, is given with poles in a union of hyperplanes of this form, okay? So in this case, it's much more difficult to talk about the roots of these guys, but they are given they are described by some linear forms, and what he shows with respect to the local zeta functions is that the poles are contained in the union of these guys. Okay. Okay. So probably you remember from the last time that the idea of the local zeta functions. So I want to make some description about the state of the oscillatory integrals with several parameters. But first, I'm going to recall a couple of things about the last time. Okay. So last time, what we saw was that we were interested in studying this type of integrals. And what we saw is that they admit a meromorphic, they admit in expansion, asymptotic expansion, in series of this form. And what was interesting is that in this case, the alpha runs through the set of candidate poles of our local zeta functions. And moreover, the coefficients appearing here are the coefficients of the Laurent expansion of the poles of the local zeta function. Okay. So one of the questions that was asked last time is how the logarithmic term here appears, where this comes from. And I think that I give incomplete answer, so I hope to provide a better insight this time. So what we have to check in order to find this asymptotic expansion here is to check the Laurent expansion of the local zeta function of its poles, okay? So the thing is that when you look at the Laurent expansion of these guys, these logarithmic terms appear. And I have an example, a very silly example here again. For instance, if you consider this distribution, this was the example that we worked it out last time. This integral defines a distribution, and you can consider this Taylor series expansion of this distribution, okay, at the regular point. And the Taylor series expansions contains these guys, okay, contains these logarithmic terms. So when you look at the Laurent expansion, what the theory says is that in order to relate this, in order to find this asymptotic expansion, you have to look at the information of this zeta function. Not just the poles, but the Laurent expansions at the poles. So when you look at the Laurent expansion, this is just the Taylor series, but the Laurent expansion will contain some terms just like this, okay? So you found some logarithmic terms and not just the powers of the parameter, okay? So this is the reason for the appearance of these logarithmic terms in these expressions. Okay, so what is the general strategy? This is something that was proved by Gusa. the general strategy is that there is some set of functions, of complex functions, that I'm going to call C, and there is some other sets, A and I. This set of that I'm calling C is a set of functions that satisfy some properties, like the properties of this guy have. So they have meromorphic functions with poles in a set of rational numbers, and they have some bounding another bounding properties. So the thing is that this zeta function belongs to this set, okay? But this set is much bigger than just these guys. On the other hand, this set A is the set of complex functions that admits asymptotic expansions, okay? Asymptotic expansions in terms of the parameters, okay? Of this form. And let's say that this expression is just one of these guys here in A. And on the other hand, we have a oscillatory integrals belonging to this family, or kind of oscillatory things here. So the thing is that the transition from this set Z to A is given by something that is called the Mellin transform. Okay, I'm going to give a couple of examples in the next slide. Okay, so the transition from this set C to A is given by the Mellin transform, and the transition from this set A to I is given by the Fourier transform. So this theorem that was relating the asymptotic expansions, let me change the color, that was relating the asymptotic expansions of the oscillatory integrals with the poles of the local zeta functions and the expansions of the Laurent and the coefficients of the Laurent expansion is just a rewriting of this general strategy of Igusa from jumping from one set to the other. Okay. So in the particular example that we considered last time, this was the oscillatory integral attached to a monomial. We construct this function gjt that was defined using the Gelfand-Leray form. Maybe you remember this. And what's happening here is that the jumping from this side to this side is given by the Fourier transform. And then what we did last time is that we changed the study of these guys by the description of the poles of this integral, and this integral is just the Mellin transform of the function j. Okay. So this was what was behind behind the results that we presented last time. Okay, so this general strategy can be used, for instance, for for studying oscillatory integrals of the following form. So remember that we were considering a map, a tuple of functions f1 to fl, and we were considering a local zeta function in several parameters. We have a description of the poles of this local zeta function. Okay, so Lesser shows that under some technical condition, and this is a big issue that I'm going to discuss a little bit later. One may prove that these oscillatory integrals with several parameters, they admit an asymptotic expansion. But the asymptotic expansions, they have more or less the thing that we expect, okay? So the form is that they appear, what appears here is each one of the parameters raised to some power alpha, and this power alpha is related with the poles of the local zeta functions, these powers alpha, and then appears some logarithmic terms of the parameter. Okay, so this is more or less what we have to expect, but it is much more difficult to relate these guys with the Laurent expansions, because we don't know what a Laurent expansion of this tuple of thing is. So it is much more difficult to say even that these guys are distributions. We can just say that they depend on the function phi. So the result in these cases are much more involved, mainly because asymptotic expansions in several parameters are much more difficult. Okay, so that was the result by Lesser, and there is also a very interesting result by Lichting in a much more recent work. Here I'm just using this a tuple of just two functions, okay, f and g. So Lichting gives a condition, the critical set of f, that is very special and it's very interesting. Okay, and I'm just want to mention a little bit about this because it's pretty technical, but essentially what he make is that he shows that for each critical point you consider a neighborhood of the point, and you can decompose this neighborhood as you can cover this neighborhood by something that he calls wedge. And these guys are defined in such a way that locally in each wedge there exists coordinates when the functions f and g are given by monomials, okay, satisfying this property. So in order to assume this, you need a family of functions that guarantees that you can actually have this expression, okay? And what he shows is that this family of functions is a finite set for each critical point of f. And he says that this is equivalent, or this can be seen as the same thing as local uniformization for maps, okay? In this case, for the map F. So the definition is a little bit technical, but the theorem is really nice because he says that okay, you can use the same strategy and try to use this fiber integral. So remember that in the one-dimensional case we put here our function gt in just one, when we were using this we have something like this, minus infinity to infinity a to the minus I t tau, and then this, and then this, okay? So in two variables, or let's say in two parameters, tau1 and tau2, what he does is that he used this this generalization of the Gelfand form, and he shows that this integral is okay, but he needs this definition of the wedges, because he needs that the inside this integral, this inner integral, you can control some the singularities of this integral, and this is done by this strange by this local uniformization property. But the thing is that with these tools at hand, what he shows is that this integral admits a very nice asymptotic expansion given in terms of the parameters. So what are these alpha? These alpha are are related with the poles of the local zeta functions of each one of the functions appearing in his decomposition of this WB. And the poles are given in expressions that looks very much the same like the ones that we saw in the theorems by Sabat and Lesser, okay? So this is a very interesting work, but again, the problem is that in several variables, so in several variables, or in several parameters, let's say, so the problem, so the expressions are much more involved. So the conditions about the critical set of F are much more involved, okay? For instance, the condition that Lesser imposes is very much very technical, okay? Very much involved. And the same is true for asymptotic expansions in several variables. So there is from a point of view, there is a lot of things to understand here, okay? But I want to move on to a couple of problems. Well, one is a closed problem and the other one is open. Related with some generalizations of the classical local zeta functions. So the first one is the following. This time I'm going to consider again a tuple, I was using this, sorry, because I'm changing the notation. I was using capital F in order to denote this tuple of k-analytic functions, but this is what the thing that we have in our article, and it was too late to change it. So sorry for that. So, but again, you consider a tuple of functions. So a L tuple of functions F1 to FL, that are k-analytic mappings, k-analytic functions, and you consider again a function with compact support and infinitely differentiable. Okay. So in this case, the definition of the local zeta function is the following. You consider here, instead of just using f, instead of considering several parameters, like in the previous case, we consider just one function, just one parameter s, but we consider, we need here something that is well defined, and we consider here the norm in KL, okay? The norm of this vector of functions. So in this case, what we get is a complex function that depends just of one parameter and is well defined, what the real part of the parameter is greater than zero. So again, you may show that this integral converges in this half plane, and moreover defines a holomorphic function there. Okay.
Wait, sorry, can I ask a question? What do you mean by the norm of f of x before?
Oh, okay. It's like, for instance, if you are over R, so if you are over R, what we have by the norm is the square root of
Okay.
fi squared, is this sum, okay?
Okay, thank you.
Yeah. Okay, so the thing is that we proof of a theorem that I'm going to show you in the next slide by using this definition, this variation of resolution of singularities, because we saw that this was more effective for our purposes. So what we use is the log principalization of this ideal I. Okay, so we consider this ideal, and by a log principalization, what we mean is the following: there is a mapping pi with the following properties. Xk is an n-dimensional k-analytic manifold. Pi is a proper k-analytic map, and this map is an isomorphism outside the common subset of the functions in the ideal. Okay. And again, you can describe this exceptional guy by this closed submanifolds of typical dimension one. You have again the numerical data, but sorry, but the numerical data in this case are just let's say one-dimensional, not like in the previous case. So, but the important thing is that the pullback of this ideal is generated by these monomers, and well, and this is the same thing like in resolution of singularities. Okay, this is nothing new. The new thing here is this. So using this strategy, what we show, or using this tool, what we show is that our local zeta function has a meromorphic continuation to the whole complex plane, and the poles are contained in the union of this arithmetic these arithmetic progressions, okay? So this is more or less the same thing that as in the one-dimensional case. So what we considered when I was what I was working on a couple of months ago was trying to understand or to relate this type of local zeta functions with some integrals. And what I had is that the oscillatory integrals that you can use here is the oscillatory integral corresponding to this function. Okay, so you may define your oscillatory integral like the oscillatory integral depending on just this function. This is just one function, but using this definition, you are able to show. I was able to show that this asymptotic integral has an asymptotic expansion, just like in the classical case, in terms of the parameters of the integral appearing here, the tau and the logarithmic term, and again the alphas here runs through the set of candidate poles of these zeta functions, and here you have a very well defined notion of the coefficients of the Lorentz functions of around a pole of this guy, so you can use this in order to find the AIs. Okay, so this is something, this is a very small result about these guys. And I want to end this presentation by by posing a couple of problems from analysis. Okay, so what I made here is to use the information that I have for a local zeta function in order to find which integral should I to consider. Okay, so this was the idea. In this type of problems, the idea is to go in the other direction. So there are some oscillatory operators. They are called multilinear oscillatory operators that were defined by Stein and Sturm, for instance, and they are defined in the following way. You consider here just one function, just one parameter, and here, instead of using your function, called that we usually use just one function depending on, this is the classical case, depending on just C infinity function depending of with compact support, okay? Depending on the n variable here. So what they introduce is they split this function in this way, just one function for each parameter, and for instance, they consider this problem just in the unitary ball, in the n-dimensional unitary box, and they assume that the functions phi I belong to some functional space. Okay, this is just saying that these guys are integrable with respect to some power of pi. Okay. But what they show is that one has the following decay estimate. So the things that we are seeing here is again some more or less things that we know. This is the logarithmic term. This is the power of tau. But what is new here is this thing. Okay, but don't worry about it. So the interesting thing is that they relate this alpha to the to the Newton polyhedron of the function f. So looking at geometric information about f, they are able to bound this thing. This is more or less the same thing that we did in the by using resolution of singularities. Okay. So, but my question is, is there an analogous zeta function for this? What would be the analogous zeta function? I mean, okay, you may think in using this function as your function f, but the more interesting question is if you can describe the terms in the asymptotic expansion. Recall that you have these terms a alpha I of phi, and they were the terms appearing in the Laurent expansions of these guys, but they are depending just of your function phi, your global function. So can you make these terms depend on every one of these phi i's? So this is, for instance, one question that we may ask. Maybe it's a silly question, but I don't know. And more generally, Chris, Lee, Tao, and Thiel defined the following oscillatory operators. Here you have the same thing, but here you have another variation, okay? This time you may consider some functions phi I depending on some of the variables, okay? In the last time, in the last slide, in the previous slide, the functions phi I depend just of the variable xi. In this case, your function phi I may depend on the, let's say, the variables x1 to xi, okay? So, okay, again, you consider some functions like this. They found some bounds for this type of integrals, but the question is the same. Can you relate this with some zeta function? I don't know if you can put this here and say something about the more from my point of view, the more interesting question is about the terms a alpha I, okay, because they depend, they are distributions depending on phi, and the question is that if you can make that these distributions depends on each one of the functions used here. Okay, and this is something that I don't know. Okay, so this was pretty much everything that I has prepared for today. So thank you again.
Thank you so much, Edwin. Do we have any questions? So actually, I have a question. So you mentioned these zeta functions with multiple parameters where, what was it? The ones of Sabah.
Mm-hmm.
And so in the in the first ones you mentioned, there was some relationship between the poles of the zeta function and the roots of the Bernstein-Sato polynomial. So is there a relationship between the roots of this Sabah zeta function and the Bernstein-Sato ideals?
Yeah, actually, is the same thing. I mean, in general, what we have. Let me go back to the presentation. So this in this case, what we have is this is just the classical case, okay? And in this case, what you have is that this list of candidate poles is in general bigger than this list. Okay. So the same is true for the zeta function with several parameters. So, but in that case, the list is given in terms of linear forms, or some linear forms appearing in the expression for the for the Bernstein-Sato ideals.
I see. And in the last type of zeta function that you consider, the one that has your theorem, is there some Bernstein-Sato polynomial you can use for the poles of these zeta functions?
Yeah, I was thinking about that. I think yes, but I'm not sure if the same polynomial of Saba will work. So I'm thinking about that. Actually, when I was preparing my talk, I was thinking what was the right definition, but
I see.
yeah, maybe that the one of Saba, I guess, but I have to write it down.
I see.
Yeah, thanks.
Mm-hmm.
Any other questions?
Yeah, so can I also ask something in connection with Imon's question, the one about several variables things, right? So the result you mentioned goes in one direction, but for example, in the case of one function, right? At least let's say you know that for the low canonical threshold, you always get a pole. Do you have such a result for several functions? So again, so for several functions, I think what I would mean is that, again, you can look at the, right? So there is a certain polytope that plays the role of the low canonical threshold.
Mm-hmm.
So can you prove that, for example, if I look at every facet of this polytope, the corresponding linear function gives me
I'm not sure. I'm not sure. I don't know. I don't know anything about that. I think. Well, I will say yes, but
so it's not known. So I would also guess that this.
Yeah, but it's not. I think it's not known. Okay. Yeah, I think that would be a safe answer.
Thank you.
Any other questions for Edwin? Okay, if not, so thanks again, Edwin, for your great 2 talks. Very interesting. And let me say, so next week, we will have Luis Narvaez Macarro from the University of Seville, and he will be talking about rings of differential operators and Hasse-Schmidt derivations. And if you want to see the abstract, it's already up on our website, so please have a look.
Thank you, everyone. And thanks to the organizers. Okay, see you guys.
Thank you.
Oh, thanks, Edwin.
Thank you, Edwin.
Thank you.
It's good how Lewis turned on his video because his name was Zen.
Yeah. Oh, Anurag said something. Sorry.
I was confused for a second. I was like, I think I saw Anurag,
Yeah.
but where'd he
So,
go?
are you
Yeah,
there?
yeah, he's over here.
That's good.
Yeah,
Okay.
yeah. Yeah, nice talk,
I
Edwin.
agree.
Yeah, thanks again for the next series.
Yeah, thanks for the certificate.
Oh, okay.
Useful.
Oh, good. There you go.
Hey.
Bye.
Okay, guys, have a nice weekend.
Okay.
Yeah, you too.
Same here.
See you all
See you.
next week.
Hello, Yusef.
Hi.
Yeah. Bye.